Good day, students. Video 20, Part C. We're so close to the end of the book. I'm excited. I hope you are too. A couple examples. We're doing t-tests, continuing with our study on those. First example here. An engineer tested 8 radon detectors of a certain model for quality control. And so what was measured, each detector was exposed to 100 PCIs over L, whatever that is, of radon in a controlled environment, and the resulting radon readings were recorded in the table. So here's the data, 105.6, 90.9, and so on. Sample size is small, just eyeballing this. I mean, how many? 1, 2, 3, 4, 5, 6, 7, I guess 8. It's definitely below 30. So we're thinking about the conditions to run a hypothesis test. I need an unbiased sample. Nothing in the problem tells me this would be biased. It was, controlled environment and all that. But with that small sample size, I need to have that normality condition met. And we really haven't encountered too many problems where we just said stop the presses. But here's one. The histogram, you can see it in your notes clearly. If I gave you this picture here and I said, please tell me if you think that these data might come from a normal model, a normal population, this is a clear-cut, no way, Jose, right? This is not normal. The QQ plot here, let me put the dots so you can see them on the video. These dots, if normality is plausible, should be close to the line, should be generally straight, and it's not, right? So all the evidence here is telling me, look, radon readings do not come from a normal population, which means I need enough data to proceed. And I don't have that data. So let's answer these questions here. Part A. An engineer would like to run a hypothesis test to determine if there's compelling evidence that the radon detectors are faulty. Well, why should you halt the process? The conditions aren't met. For Part A, conditions are not met. Stop, right? N equals 8, which is way under 30. Need normality. And guess what? We don't have it, so we can't run the test. The methods we use in a statistics course, all these tests and intervals, certain conditions need to be met. Or what you're going to do is it's basically like bad information in, bad information out. You run the test, you can't really trust in the results. So we've got to stop, conditions aren't met. And the clear suggestion here, what suggestion could you give to the engineer? You have to collect more data. Plain and simple. If you want to use a t-test to test a population mean for these radar detectors, we need more data. The conditions just aren't met. So for this problem, we're done. We can't run the test. Always be aware of that. I'm sure in class that we're going to present you some problems every once in a while where maybe we're not throwing you a curveball, but you've just got to be alert that conditions aren't always met. All right, let's flip the page. There's a second example where the conditions will be met and we'll be able to run the test. So over to the back side. Again, if the data are here, this is a pretty small sample size. An office building fire sprinkler supplier runs a test to determine if their sprinklers activate in under 30 seconds. So that makes sense. If there's smoke or heat, definitely want the sprinkler system to kick on quickly. 13 sprinklers were tested this month. Can the company still maintain their claim that, hey, in under 30 seconds these things kick on? That's what they claim in their advertising. The data are here. Graphs are below. You can see the graphs. Run the hypothesis test showing all steps. All right, let's pick out couple of nuggets of information here. I'm seeing the words on average here. It's sort of cluing me in that I'm running a test for means. The data is quantitative, right? The variable is what? Time in seconds. So we start the clock and maybe we introduce a heat or smoke source and we just wait until the fire sprinkler kicks on. So we have a quantitative variable. Sample size pretty small. We said n is 13, so we know what we'll need to do. We will need to check for normality. All right, I bet I got the pictures on the next slide here. And I do. Make a histogram. Could you imagine this data coming from a normal model? I mean, with 13 data values, it does seem like most activation times are piling up here in the center, and it's tapering off from the tails, so I'm feeling pretty good about it. Over here, you've got the dots. I'll fill them in for the video, can pick them up, and this looks a heck of a lot better than the previous one, right? In general, it's never going to be perfectly straight, but those dots are awfully close to that diagonal line. There's really no wavy patterns to the data, and I would be comfortable with my small sample size of 13 to make that normality assumption and go ahead and run the t-test. Okay, so we're going to do it. Oops. Yes. I'm going to need to add a blank slide here. Let's see if I go a little space to right. All right, so video will pick this up a little better with the light on it. All right, we're going to run the test. So just quickly up top, conditions. Assume the sample is unbiased. Nothing in the scenario description made me believe it was biased. And also, data look normal. So the conditions are met to run this test. Now, here's what you would need to do. Take those numbers, open up StatCrunch, type them into a column, and get those summary statistics. Not every problem will you be presented with, hey, here's Y bar, here's S, and so on. So, here's the summary stats to run that test. These came from StatCrunch. Pause the video. Make sure this is week 2 stuff. You've got to be able to do this, right? And the sample mean here was 26.692 seconds. Remember what the claim was? Do these things kick on under 30 seconds on average? And so that sample mean is under 30. Is it convincingly under 30? Sample standard deviation S for this problem was 4.442 seconds. All right, so we've got our mean and we've got our standard deviation. The hypotheses, H sub 0 and H sub A. I like to do the alternative first. This is what I'm testing. So we're testing means, we put mu. And the claim up in the scenario says, can the company still maintain their under 30 seconds claim? Under 30 sure sounds like less than, so mu less than 30 seconds. Up in the null, we always put equals as a convention. Really sort of what we're saying up in the null is it at least more than 30 seconds, 30 or more, but we'll put equals up here up top. And we're looking for the evidence from the sample that we can still claim it, that it's under 30 seconds. All right, I believe you've got a whole blank page there. Don't try to squeeze this in at the bottom on that half page at the bottom. You've got a whole page. Let's see, I think I'll erase everything and start with a clean slate here. So pause the video if you need to catch up. Hypothesis testing, same steps every time. Get the test statistic first. Get the p-value second. Make a decision, write a concluding remark. So, test statistic time. Test statistic. We're always running t-tests for means. Remember the formula is y bar minus mu sub 0 divided by s over square root of n. So the numbers we have, I had erased them, but you've got them written down. Sample mean y bar was 26.692. We subtract off the 30. We divide this by S over root n, it's the 4.442 over square root of 13. And this turns out to be, this is our t, it's negative 2.685. Now we're running t-tests, so those rules for z-scores aren't always, in play, but our sample mean was almost 3 standard errors below 30 seconds. And 2.685 standard errors. In our heads, we're already thinking, all right, I've got something here. This is pretty unusual, but we've got to shade under the t-model to get that p-value, which is a probability. Okay? Don't make your decisions based on the test statistic. Always make them on the p-value. Test statistic first, p-value second. Draw this picture in your notes, students. Don't get lazy. Here's a t-curve, degrees of freedom 12, right? Because the sample size was 13. Subtract off 1, gets you down to 12. T-curves are always centered at 0. And if I was going to draw this picture, and you are too, put the test statistic on that model and shade in the direction of the alternative hypothesis. So negative 2.685 is going to be down here somewhere. I need to get this stuff. You know how to get it. You've got to go to the step crunch tool. You've got to pull up that t-calculator. Pop in degrees of freedom 12, shade left, less than, and this here is the p-value. From the step crunch tool, what do I get? I have no idea, but here it is. 0.0099. That's the p-value. Okay? Pretty small, right? We're less than 1%. I'm going to look at the sheet here. Does anywhere tell me a significance level? Like run the test alpha 0.05, run the test alpha 0.01. I don't see it. By any standards, this is pretty small for a p-value. And so you know what you're going to do, right? You're going to reject the null, and we're going to conclude that the company's claim is still valid, that on average these fire sprinklers kick on in under 30 seconds. All right, a few things to write. I'm going to erase the board. All right, there's my small p-value decision. The decision is clear-cut, reject the null. Remember what the hypotheses were. I know you can flip back, but mu equals 30 seconds. Versus mu less than 30 seconds. I reject the null. How come the p-value is small? We have a sense of p-values, right? You can put if you want. It's under 0.01, right? It's less than 1%. We do have sort of overwhelming evidence for the alternative. Conclusion and done. So what's the conclusion? There is evidence that the company's claim is true. There is statistical evidence. There is evidence that the mean activation time is still under 30 seconds. Conclusion, there is evidence that the mean activation time is still under 30 seconds. So I guess if the company sort of runs tests every so often and makes sure that the sprinklers are still working like they're supposed to, they can feel confident putting this claim when they send the salespeople out trying to get new fire sprinklers installed in office buildings and homes and things like that. All right, I believe that wraps up the whole lesson 20, short one A, B, and C. So thanks for watching, and we will see you in class.